Okay, all right, guys. So we're going to start with this a little bit of a review. And today we are going to see a lot of exercises, and then we're going to go through those exercises together. So you will have a better sort of like a idea and a feeling of how things is about to happen in first law of thermodynamics application. Yeah. All right, so we're going to start with this one, warm things up from last time. So if you remember a little bit that we kind of like down to a couple of or only a handful of processes that we're going to consider mainly. One is like this: constant volume, constant pressure, constant temperature, and no heat flow, for example, right? So those are going to be like the key processes that we are going to focus on. And the rest could be a little bit of add-on from time to time, but just sort of like be familiar with these four. It's going to take you a lot of sort of like a understanding in thermodynamics. It's sort of like take you very far already. Okay, this one, you have 1 mole of ideal gas. All right, here we go. So with that, then that means you already know this is n, the small n, number of mole is equal to 1. All right, and it does 3,000 joules of work on the surrounding. So this is the information of the W, which is just to confirm that we talk about the W of the system. So gas perform works on the surrounding. So this is the work done by the gas. So that is the amount of work done, W, that we have been using. As it's expand, all right, so I know now that it's expand, and the key is an isothermal process. So this is the key. So this indicating what type of process that we are dealing with. This is an isothermal process. So you know that this is going to be a constant temperature. All right, good. And the information given next is the final pressure is given and the final volume is given. Because it's a final, so it means that's not an initial value. So let me put subscript there just to indicate that, hey, this is a P2, this is a V2. Okay, that's a final state of our gas. So determine the initial volume and the initial temperature of the gas. So what they want to know is what is V1 and what is the temperature. But then it doesn't matter is it T1 or T2 because T1 and T2 must be the same. You guys with me? Because it's an isothermal process. So temperatures stay fixed at all times. All right, cool. So what do we do? All right, so this is the type of thing that you have to start to get used to. There are so many information available to you at the moment. Like so many things, so many numbers, so many parameters, and sort of like a processes type and all this stuff. So that's why first thing first, it's an isothermal process. You come back and think of this one. And if you remember, what we did before was just like when you have no temperature change, it's a guarantee that no energy change. Delta U is 0. Okay. And when the delta U is 0, heat and work are exactly the same. We calculated the area under the curve to figure out the work done. So we already integrated once. You don't have to do it again. You can stick with this formula here. So the amount of work done by the gas can be calculated from nRT log V final over V initial, for example. Okay, so this one, you can write it down in your personal notes, bring it into the exam room. That's fine. You don't have to do the math again. So over here, I'm going to use that one. So W in the isothermal process is nRT log of V final over V initial. All right, so these are probably the things that we're going to need. So what can we do? They want to figure out the initial volume and the initial temperature of the gas. But the good news, if you look at this, Adan, we already got pressure, volume, and the number of mole in the final state. With me? All right. So by knowing this, well, Adan, why don't we start with the equation of state from PV equal to nRT, yeah? So if we get this, then, oh, okay, that, okay. So if you talk about the state number 2, that would be great. So from here, this allows you to calculate the temperature already. You guys with me with this? Yeah, so from here, well, okay, so T2 can be found right away. Nice. So this is the kind of thing that you just have to observe a little bit and sort of like, oh, we have enough information to evaluate the unknowns from equation of state. So we just grab that opportunity and do that right away. So P2, so let me put it there. All right. So in the exam, I will try to stick with the SI system. So in this particular exercise is in ATM and liter. Usually they use in chemistry, but don't worry about it. We're going to try to stick with that. But from here, I can convert briefly is 10 to the 5th Pascal. And this one, if I turn it into cubic centimeter, I have to multiply by the -3 to get to the cubic meter. All right. So a little bit of units conversion, just incorporate it in there. So now I can do, all right, so let me move things a bit. Here you go. Okay. All right. Okay. So P2, 10 to the 5th. Okay, let me just ignore the units for now, save some space here. Volume, 25 times 10 to the -3. The number of mole is 1. And R, we can just leave it as R. That's okay. All right, if you don't want to substitute the numerical value, that's fine. I think leave the R in the equation is not that bad. So that's it. So let me at least get a little bit of cleaner numbers. 2500 over R. Kelvin. That's it. Done. So that is the temperature. Okay. And definitely this is going to be the T1 as well. T1 is going to be the same as T2. So T1, T2, they're all the same. Isothermal process. Okay, nice. All right. So with this now, to figuring out the initial volume shouldn't be a problem anymore, because if you take it from here, well, done. All right, work done is nRT log V final minus V initial divided by V initial. But now we know everything already. So we can just substitute it in. The work done is 3,000 joules. nRT, and now you can do anything you like. You can just substitute temperature that you just found out here. That is fine. Or you can use P2V2 here. That's good too. You guys with me? Got it, right? Because it's a PV is always equal to nRT. Doesn't matter. Just use anything you like. So over here, I can maybe just substitute directly. N is 1, R is R, temperature is 2500 over R. There you go. No matter what, you're going to get the same numbers out anyway. And then you get log of the V final that you want to figure out, a V initial that you want to figure out. So divided by V1, but then the initial volume is 25 times 10 to the -3 cubic meter. Everyone good? Yeah, just using this expression, the only unknown left in this expression is just V1. So your job is done. So over here, V1 can be found. A little bit of calculator would help. And you saw cancellation already here. Leave it as R. It's kind of nice in this way. So pretty much R just disappear. You only have just a little bit of numbers to figure out. Not too bad. Okay, okay, reasonable, reasonable. But this one is just giving you an idea that this is a stuff that we sort of kind of like, okay, that's thermodynamics. There are always going to be a lot of info available to you. And because you have pretty much like a handful and quite a lot of formulas, expressions that you need to bring in as well. So that is a part that is annoying. But other than that, in terms of the level of difficulties in mathematical technicalities, pretty low. You only have just like a linear equations most of the time. A little bit of algebra, a little bit of logarithmic functions, not too bad. Okay, sounds good? Not bad, not bad. All right, so today we're gonna keep doing this, okay, until you don't want to do it anymore. That's a good sign. Okay, so when you do it until you kind of like get sick of it, then you start understanding it. All right, guys, try again. Next one. So things will progressively more difficult. All right, eventually we're gonna get to a full features problems where you have to calculate everything. But let's sort of like climb up the difficulty level 3 a little bit here. The figure shows a PV diagram for an ideal gas, which is absolute temperature at B is 1/4 of its absolute temperature at A. All right, just this information alone, what are you having? You get T at B is T at A over 4. Temperature at B is 1/4 of the temperature at A. All right, leave it there. That is one piece of information. What volume does this gas occupy at point B? Oh, so look at this. That is not too bad. The question A only asks you about the state of gas. So you probably don't have to think about thermodynamics just yet. Just use state of gas equation. So let's do it. Well, okay. From PAVA over TA equal to PBVB over TB. Looks good? All right, because, well, you just want to know what is going on with the gas when you change some quantities, yeah. And the good news about this one is the horizontal process. So that means the pressure is fixed. So definitely pressure are exactly the same. I cancel that out. Okay, however, again, as well, because you already knew that the temperature at B is 1/4 of temperature at A. So you use that ratio to figure it out what is supposed to happen here. The volume is supposed to be 1/4 as well. Sounds good? Make sense? All right, so okay. Or if you want to write it down properly, V at B over V at A is going to be T at B over T at A. And it's going to be 1/4. So that means you can write down the numbers right here right away. So the volume at B is definitely 0.125 liter. All right, cool. So by knowing this, your PV diagram looks good already. You pretty much know all the points, point A, point B, values of the pressure and volume. And a little bit of temperature now we know is 1/4, right, between B and A. All right, so that's good. Let's move on, part B. How many joules of work was done by or on the gas in this process? All right, so I think that was a redundant sentence here. All right, here we go. All right, you want to know the work done? All right, I'm okay, I remember that. To figure out the work done, you need to just figure out the area under the curve. And because it's just a constant pressure process, the area under the curve is just a rectangle. Okay, let's go for it. So part B, work done by the gas is integral P dV. But because we know pressure is constant, I can pull P out. The integral of dV is simply just a change of the volume. Just to confirm again, is going to be just the height times the width. Okay, keep going. The height is good. That's a P. The width is good. That is your delta V. So just multiply them. So let me keep the ATM and liter units for now. We can always change it later. This is just to showcase that you can do this easily this way. Here we go. All right. And then, all right, if you want to convert the unit, all right, so this is ATM, this is in liter. So if you want to convert, it's gonna look like this. Times 10 to the 5th, turn it into Pascal. Turn liter into cubic meter, you have to multiply by the -3. All right. But notice this, it's a guarantee that, hey, Dan, wait a second. Remember, we focus on this one a lot. It's the delta V. So it's going to be the V final minus V initial, yeah? All the time, yeah? And look at this. It's a contraction process. This one is the compression of gas. Gas is actually get compressed. So the final volume is actually less than the initial volume, yes? All right, so if you keep the order of subtraction correct, the sign in front of 0.375 is supposed to be negative sign. Everyone good? Okay, volume in the end is actually less than the volume initially. So if you keep that in mind, then you have to make sure that your answer is supposed to be a negative work done. All right, that is the key point that we want to make. Okay, don't forget that you have to take the sign properly, because the expansion process and compression process will give you the opposite work done, or whatever the process that is happening, positive and negative, is pretty much opposite. Okay, looks good. All right, so that's it. So that is the amount of work done going from B to C, B to A. So if you want to be clear, sometimes we can put the subscript here as well, WAB. You're going from A, did I say B to A? Sorry, A to B. You're going from A to B. You can put like WAB in there just to confirm that you want to go from A, you want to end up at B. Right? That helps a little bit. Okay, not bad, not bad. All right, so now you figure out the work done, which is, all right, negative as expected. Part C, did the internal energy of the gas increase or decrease? All right, they're not asking you to calculate yet. They just ask you, is it increase or decrease? That's all. But don't worry, today we're gonna eventually calculate everything. But for this particular example, they just want to know the direction of change. They are not asking you to figure it out just yet. So part C, guys, what about internal energy? That is the U, yeah? Does it change, increase, or decrease? All right, so the trick that we talked to you about last time, remember the isotherm, the constant temperature line? Every point on this PV diagram must be on an isothermal line all the time. Oh, missed it. There you go. Right? Okay. So, okay, Bajan. So if by just looking at this, you're coming from A, you come down to B, you are jumping down, coming from a higher lying isotherm to a lower one. So guarantee that the temperature must be dropping. So this is a higher temperature. This is a lower temperature. So what it means is in part C, the delta U must be dropping because temperature is down. Everyone good? Okay, you're coming from point A to point B, you are jumping out from the higher lying isothermal line, so it's in higher temperature, down to a lower one. So with that, your temperature drops, your delta U must be negative for sure. Okay. So U decrease. All right. And what about part D? What about heat? You want to know heat. Is it enter or leave the gas? All right, so usually no big deal done. To figure out the heat, you now bring in the first law of thermodynamics. All right, so I just moved W to the, okay, if I want to be clear here. So first law of thermodynamics, we write it like this. Delta U equal to Q minus W. So your heat is just the sum of the delta U and the work done. But we have already found out that the work done is negative. The delta U is negative. So it's a guarantee that the Q must be negative as well. Okay, okay. All right. So Q is negative. So heat leaves the system. Done. Okay, not bad. So that is the idea that what we really need to do the calculation with in any problems. You usually want to know everything. When I say everything, there are only three things: work, delta U, and heat. Those are the three key components in our first law of thermodynamics. Make sense? All right. But this one, you only do the numerical value on just work. But we'll do everything eventually today. But this just warm things up just a little bit more. Okay, very good, very good. Getting better. I know. All right. If this is good, ready for the next one. All right. If possible, maybe you want to give it a shot. I'll give you a couple minutes to think about it, and then we'll go through that together. All right, next one, guys. Here you go. Another PV diagram. An ideal gas is taken from point A to point B on the PV diagram shown in the figure. All right. During this process, there is a 700 joules of heat is added, and the pressure doubles. All right. So those are the two information that's given to you. There's a heat and there's a double of the pressure. All right, just by this alone, you should be able to say, oh, okay, John, this is fine. Point B must be at 60 kilopascal because it's doubled the pressure. All right, as usual, we go on and on with each sub-question. How much work is done? Oh, John, not a big deal. Vertical line, no work done at all. So let me put WAB is simply 0. Got it, right? Vertical line, no volume change, no work done. That's it, 0. Part B, how does the temperature of gas at A compare to its temperature at B? Right, you want to give it a shot? If you think quickly about that, again, it's not asking something about thermodynamics. I mean, it's not one of the 3 components in our first law of thermodynamics equation. It's only asking you the state of the gas. Very good, very good. Right, so John, why don't we just use equation of states? You know, because we are not sort of like into the dynamics just yet. So if you think that way, then that seems to be right. P A V A over T A equal to P B V B over T B. Yeah. All right, that's sort of like a boring relationship at this point. But the good news is the volume is fixed. So volume does not change. Gone. So you should be able to tell right away from this, because the pressure is doubled, your temperature is supposed to be doubled as well. Okay? All right, so that's it. They're asking for that. How does the temperature at A compare to at B? Okay, T at A over T at B is going to be half. Not bad, not bad. Okay, and once again, in your head, you're supposed to think just like before. Point A and point B supposed to be on one of the isotherm all the time. Okay, and because A is definitely lower, it must be on a lower isotherm, so the temperature must be lower, and now we know exactly it's lower by 2 times. So the temperature at A is only half of the temperature at B. Nice, nice. Part C, how does the internal energy of the gas at A compare to the internal energy of gas at B? So now you need the numerical value. So let's give it a try. Part C. What they want to know is U at A over U at B, right? That's what they want to know. How does the internal energy of gas are compared? And the good news about this one is, remember that we have a fixed relationship between the U and the T all the time. 3/2 nRT. That's how you use this equation right here. The internal energy is always 3/2 nRT for monatomic ideal gas. So we always gonna use this equation here. And once again, the gas constant and the numbers in the front just cancel out. So it's just a ratio of the temperature as well. Because the temperature is twice at B, so over here, it's gonna be exactly the same ratio. So the internal energy is also half relative to U at B. Sounds good? Not bad, not bad. And actually, one missing questions that actually I can just ask you right away if I want to is just an extra question is, can you figure out the delta U going from A to B? What do you think? Well, then, of course, because, all right, delta U going from A to B equal to heat going from A to B minus work going from A to B, yeah? First law of thermodynamics all the time. But because this one we know there's nothing going on with the work, so that means the delta U must be exactly the same as the heat. But the information is already given there. Heat is added. So it means it's a positive heat flow into the gas. So I can tell exactly that it's going to be positive 700 joules of heat. And that must be delta UAB as well. Looks good, guys. Not bad. All right. So if you want, you are going to be able to calculate exactly how much internal energy U is supposed to be, because now it's going to show you with the two equations. In part C, you know the ratio between the U, and in part D, or I mean the star part here, it gives you the difference in the U. So by solving these two, you should be able to figure out U A and U at B for sure. Okay, but they're not asking, that's okay. But this is just an idea that if you want, you can do it. Getting more and more. Looks good. All right, or I can write it down for you so you can see a lot easier. U at B minus U at A is 700. So if you combine equation number 1 and equation number 2, you should be able to solve for U at A and U at B. Okay? All right, if you want to. Not bad. Not bad. I don't know. Maybe it's already bad. All right. Very good. Pretty nice. Pretty nice. Okay. Okay. All right. Now let's get more challenging problems. And here you go. All right. This now is going to get more complicated because now you're going to have a multiple sections or multiple segments processes now. This is only like a single segment, so like just horizontal, vertical, everything is good and nice. Here, now you have a multiple processes, things are going to get a little bit more complicated. How? Let's take a look. The PV diagram shows a series of processes now. The information here is in AB process, 150 joules of heat is added. All right, so that's one piece of information. All right, and in the BD process, is a 600 joules of heat is added. All right, just leave it there. Just good to know. Good to know. All right, from the PV diagram, and it looks pretty complete. That's a good thing. You know the pressure and volume at all points. Okay, so it looks good. Part A, figure out the internal energy change going from A to B. All right, guys, you want to give it a try? Delta U, A, B. Which, just to confirm, is U at B minus U at A, just to confirm. Right. You want to go from A to B. All right, so let me highlight this one as the yellow portion of this process. You want to go up right there. All right, A to B. All right, how would you do it? Bojan, good. You only have a single equation to evaluate U, which is, all right, so let me put on the side right here. U is always 3/2 nRT all the time, all the time. All right, so with that, what I can do is a 3/2 nRT at B minus 3/2 nRT at A. Good, good, good. All right. But then again, Majan, I do not have the information about the temperature, which is okay. Why? Because here we go. nRT is PV. So I can turn nRT into the product between the pressure and volume. See, so that is the utilization of the equation of state at all times. So you can just convert back and forth and you know exactly what are the pressures and volumes at all points. So we should be fine at this point. All right, let's give it a shot. So it's going to be 3/2 P at B. So take a look here. 8 times 10 to the 4th Pascal. V at B is 2 times 10 to the negative 3 cubic meter. Very good. And then you're subtracting with a 3/2 pressure at A. 3 times 10 to the 4th. All right, so let me ignore the units here, save some space here. 5, oops, sorry, take same volume, 2 times 10 to the negative 3. Here we go. Pretty good. All right, all right. Let me work out the number here a little bit because we might be able to reference this in the future. So this is 2. This is 5, 15, 150 joules right there. If my math is right. Yeah, okay. Okay, very good. Okay, 150 joules. That is the delta U going from A to B. See, not bad, not bad. It's doable, doable. Now, here we go again. Part B, well, hey, we want to go further. What about the internal energy change going from A, B, D? Ooh. You want to go A, B, D. So you want to go a little bit further away. But then you guys remember one thing? Internal energy is path independent. Okay, so actually it doesn't matter. You want to go A, B, D, you want to go A, C, D, or you want to go A, whatever D. You start with A, you end with D. Yeah. So over here in part B, delta U A, B, D will be exactly the same as a delta U A, whatever D, doesn't matter, because it's only going to be U at D minus U at A no matter what. Yeah, it's path independent. Energy don't care. I mean, where you get there, it doesn't matter. In the end, the state of the gas is what matters. All right. So over here, you have 2 ways of doing it. You already got 150 from part A, but can we just add like a BD process and only do the delta U from B to D and then add to part A? Yeah, you can do that too. All right, but well, why do we want to complicate ourselves? Because we already know that it's just the initial and final point anyway. So I was just gonna start over again, so not big of a deal. So I start with the 3/2 nRT at D minus 3/2 nRT at A. Yeah, we're just gonna do that. And substituting everything just like before. So nRT is just PV. So I can just do that again. Here you go. All right. And once again, substituting the numbers, not big of a deal. So going from A to D, I know all the pressure and volume. So let me substitute D, point D first, is 8 times 10 to the 4th, 5 times 10 to the negative 3. Oh, let me move to a new line here, let out a space. There you go. And subtract out 3/2 at point A, P is 3 times 10 to the 4th. Volume is 2 times 10 to the negative 3. Here you go. It's just exactly just like part A. No big of a deal. Just different points. Okay. All right. And now a little bit of numerical value. All right. So let me look at this. Okay. That's 40 minus 6. So that's 34, 510 joules. All right, if I get that right. Is that right? That doesn't look right. That's 9. That is 60. 6. Oh, okay, that's good. That's good. All right, 510 joules. All right. Perfect. All right, here comes the last part. What about the total heat going from, oh, whoa, be careful here. Now they want to go A, C, D. So there's a different path again. They want to go the red line here, A, C, D. What is going to be the heat added during this process? Well, done. Wow. What can we do here? No big deal. First law of thermodynamics will help. All right, so let me squeeze this down a bit. All right, part C. So what we're going to do is, all right, guys, you want heat, right? From delta U equal to Q minus W. So heat is the delta U plus W. All right, we kind of see this like many times now. But the delta U, you already found out from part B. Got it? The same thing here. With me? Right? Because it's path independent. So you want to go A, B, D, or you want to go A, C, D, the delta U must be exactly the same amount. So you can reuse part B answers for this portion of part C. The delta U is exactly the same. Everyone with me so far? So the only thing left for you to really calculate is what is the work done, Ajahn? If you know the work done, your job is pretty much complete. And what is the work done? Area under the curve. Ooh, right there. That's it. Okay, with me? So what you can say is, this is simply just the shaded area. The delta U here is the same as 510 joules. No biggie. Okay, okay. All right, so let's do that. So it's going to be equal to 510 joules. That's coming from part B. Plus the area of that part, it's only cover AC and below. The vertical line won't contribute anything. So you just do the width times the height. So that's good. 3 times 10 to the 4th plus positive change of the volume. Okay, so let me write it here just to confirm. It's a P delta V, the width times the height. And the volume increases because it's an expansion. So that's why I emphasize with the positive sign, 3 times 10 to the negative 3. And that's it. It's done, guys. It's 600 joules. Bam. Woo! How do you like that? Not bad, I hope. Okay, so up to this point, we pretty much like halfway done in the sense that you start to see that there are so many things that can be questions. You want to ask, you want to figure this out here and there. You want to use equation of state from time to time. You want to figure out the change of the U. You want to find out the work done. And eventually, from the look of it, heat seems to come last. Right? It seems like you use sort of like the idea of, hey, area under the curve. Can I figure it out? Easy. Hey, can I use U equal to 3/2 nRT? Yes. So it seems like work and the delta U seems to be the first two that get calculated first. And then heat seems to be sort of like a byproduct after you have already done the other two. Yeah, because the other two have a sort of like a definite relationship with something else. So it's easy to calculate. But seems like heat, the Q, rely on the other two most of the time. That is pretty much the order of execution that you usually have to do. Okay, sounds like a good plan. All right, even though you just all right, I kind of get a feeling of it, but don't worry. After the break, we'll do like a grand finale of today. We're gonna do like a big whole chunk of the PV diagram, okay? And we're gonna do everything this time, even though they try to ask you this and that, but I'm going to show you what if I want to know everything about the thermodynamics that is going on in this process. What can we do? Okay. And if we can do that, then we get a complete picture of what's going on with this process, and we just be able to answer anything that we want. Okay, sounds like a good plan. All right, but anyway, at this point, let's take a break. All right, we'll come back with like a big exercise right there. All right, the next one is the big one that let's go through the question first. And I'm going to approach this question in a sort of like a full format. I'm just going to calculate everything. So you will be able to pretty much see all the components that gets calculated here. And we're going to wrap up with some conclusion. We can learn a little bit from this. And we're going to sort of like amplify that understanding again next time. So this is good. All right, so this is sort of like an ultimate question that I said before that I love this type of questions because it allows you to see the dynamics, both from the mechanical side, which is work, and the thermal side, which is heat. Okay, and now in combination of this, you get a cyclic process, the process that run in cycle. So this one start to sort of like reflect what is going on in heat engine, like an internal combustion engine in your car. It runs in cycle all the time. Okay, you draw in the gas, combust the gas, burn it out, draw the energy, turn the wheel, and just sort of like repeat that process over and over. So you get a machine. Okay, so this is what is happening here. The graph in the figure show PV diagram for, okay, good, 1 mole of ideal gas. So that is giving you N equal to 1. Okay, the CA of this process is given to be isothermal. So that's also a good idea that we just overlay isothermal line on top. Why not? Just to sort of like tell ourselves that, hey, that is the constant temperature line. So find the pressure of, oh, the gas is helium at point A. All right, part A, you want to know the pressure. This one is not thermodynamics just yet, just the state of the gas. So, all right, no problem. Part A, we have seen this before. So what you can do is, you just said you want pressure at A. What you can do is PA VA over TA equal to PB VB over TB equal to PC VC over TC. Yeah, something like that. It's just like boring stuff. Chemists do this all the time. No, just kidding. All right, but the point is, now you can pick any points in the diagram. You only have 2 points, A, B, or C, but doesn't matter. This equation works at all points. So you can pick maybe A and C, maybe they are on the same temperature. So if you pick A and C, temperature will be canceled. Or, Ajahn, what about B and C? Yeah, that's good too, because it's a constant volume, something like that, right? So do anything. So if I want to pick B and C, all right, so if I do B and C, this pair right here, the good news is volume cancels. Okay, something like that. And what else, Bajan? If you do that, then it might not work so well because you know the pressure and volume at C. Oh, yeah, it works too. All right, so we just substitute the numbers in. All right, let's see what we have. P at B, that's what you want to figure out. T at B, Bajan, I don't know the temperature. You see that? So that's why it depending on the types of points or whatever that make things kind of like a little bit easier for you. If you picked to compare B and C, it seems like, it doesn't seem to work because we don't know the temperatures just yet. Something like this. All right. So your choice. But let's do this pair. A and B. The good news about A and B is the pressure are not this. I mean, the pressure cancel. But that's kind of bad because if you pick A and B, the pressure just disappear. So you won't be able to evaluate that anyway, right? So that allow you to just, the only place that might conveniently allow you to figure out the P at A is A and C. So let's do that. So I'm just gonna pick this pair. So let me rewrite it everything again. So, okay, so let me do this. I'm just gonna erase this, get this pair right here, P and C. Okay, let me start over here. So from that analysis here, so what I should try, probably P at A, V at A over T at A, and what's going on at C. Something like this, all right? So we just play around with the equations that we already knew, and sometimes if you got stuck or it doesn't get you so far, just move back and then do something else. All right. It was just, there will be some point that allow you to progress anyway. All right. So over here, T cancel. Oh, that's good. All right. So with this, then now you can calculate the pressure at A. So that's easy now. P at A is, but from the look of it, Ajahn, it is kind of conceptually simple here because the volume at C is 4 times. The pressure at A is supposed to be 4 times as well. Make sense? Because P and V stays fixed at all times. So actually, you don't have to sort of like think too much. You know exactly this is supposed to be 8 times 10 to the 5th Pascal. Everyone good? All right. So, or if you want a direct substitution, that is fine too. PCVC over VA. There you go. And you just substitute things in, and you're going to get 8 times. Okay, looks good. All right, part A is done. You figure out what is the pressure at A, which is pressure at B as well. Part B, they want to figure out the temperature at all points. Can we do that? Well, of course, we definitely can do it because we want to know temperature at all points. So we start using PV equal to nRT. The reason for that is because we know all the pressure, all the volume, and we know N. So once we know 3 quantities in this equation of state, we figure out the rest, the temperature, the 4th one. So that is fine. So what we get is the T at A is going to be PAVA over NR. Okay, very good. All right. Substitute the numbers. Okay, so let me move this to the left a bit. There you go. No, shoot. 1 second here. Just want to. All right, that looks fine. Okay, so pressure at A, 8 times 10 to the 5th. The volume at A, 0.01. Pressure volume, N is 1. And we just leave R there. Just, no, I don't need to substitute R. R is nice by itself. So T at A in conclusion is going to be 8,000 over R. But knowing the temperature at A is the same thing as the temperature at C. So your job is pretty much almost done. All right. And you do the same thing for the temperature at B. So T at B is going to be PB VB over NR. And I can do a quick math over here. At point B is 8 times 4, 32. It's going to be 32,000 over R. Done. That's it. So those are the temperature. Even though it looks weird, it looks under R. But if you substitute R, you can calculate the temperature in Kelvin. But I think I love to just leave R as is because eventually we can be able to use it for cancellation in the future calculations. All right. So part B is not a big deal either. So part A and B is simply the usage of the equation of states. Now, the major question will be part C. How much heat enter or left the gas during A, B, B, C, and C, A segments in the process? Now, you want to know everything. What is the heat flow in or out in each segment? Okay. And if you move on to the next page, they want to know how much internal energy also changed during each segment. So to be able to answer everything, so I'm just going to do this. Well, instead of answering that question one by one, I'm just going to show you this is what we're going to do. I am going to go through the process each segment at a time. Let's go A, B first. Okay, okay. And I'm going to process everything. When I say everything means there are only 3 things. The work, internal energy change, and heat. That's it, right? You only have 3 things in your first law of thermodynamics. Why don't we just do everything then? So AB, let's do WAB first. That's always the first one that we can attack because it's area under the curve. So, Bajan, that's good. That is going to be this area down here. Okay, good, good. So it's going to be P delta V. It's going to be P V at B minus V at A. Everyone good? Final minus initial point all the time. The pressure is good. 8 times 10 to the 5th Pascal. The volume change, you go from 0.01 to 0.04. So it's 0.04 minus 0.01 cubic meter. Here we go. And you're expecting to be positive because gas is expanding from A to B. Okay, so that's good. Mathematics give you positive numbers. That's nice. So that's it. So it's a 24,000 joules. Here we go. Am I right here? Yeah, I hope so. It's 0.3. Okay, all right, that's it. So work done going from A to B is just area under the curve. And we got it 24,000 joules. Okay, what else do we know? Well done. I remember U is something that we can deal with. Okay, so why don't we take the delta U, the change of the internal energy going from A to B? We have exact formula for that. It's going to be U at B minus U at A. Everyone good? So let me zoom in a bit. Here we go. And we know exact formula for that. 3 half nRT at B. And actually, I'll just wrap it as a delta T like this. Because you're going to have 3 half nR as a common factor anyway. All right, very good. Keep going. But then, Ajahn, we already knew the temperature at both points. Yeah? So substitute it in. Why not? Okay, go for it. So what you can do is now 3 half N is 1, R is R. Temperature at B, take it from part A, 32,000 over R. Temperature at A, 8,000 over R. Very good. All right, and as you notice, R cancel. That's lovely. And what you have left is, okay, 36,000 joules. Got it? All right. So the good things about this one is you start to see what I'm trying to do. You're going from A to B. You do everything, work done, delta U, and of course, heat will pop out in the end from these two right away. Ajahn, Q from A to B is going to be delta U plus W from first law of thermodynamics. So you just add these two numbers together, your job is done. Bam, there you go. That's what I meant by complete pictures, right? Because in the first law of thermodynamics, you only have these 3 quantities in the equation. So now you know how to calculate each piece in that equation. So why don't I just do them all? And then in the end, I just pick the answer. You want to know the heat flow, you want to know the change in the internal energy, you want to know the work done, just grab the numbers and answer. Sounds good? All right. But double check again. Does it look kind of like they all make sense to you? Well, yeah, work done is positive because it's expanding. The delta U is supposed to be positive too, because once again, point B is supposed to be on another isothermal line. Yeah. Going from A to B, you're jumping up higher in isothermal line. So, oh, yeah, the delta U is supposed to be positive too. And when both W and delta U are positive, heat is positive. So heat flow in to the gas during this process. Nice, nice. All right. พอได้ไหม? No, not bad, not bad. All right. Start to have fun, yeah? Yeah? All right, okay, okay. Not bad, not bad. All right, try again, guys. Let's go from B to C, shall we? All right, so let's move from B to C. So let me highlight blue here. B to C. All right, so let me go on to the next page right here. We're going to go from B to C. Here you go. All right, so let me highlight blue over here. That's B to C. Okay. All right, the good news about this one is, well done, I love it. It's a vertical line. Work done is gone. No work done. No volume change. What else? Oh, delta U comes up nicely. It's going to be U at C minus U at B. All right. And whatever this thing is going to give you the heat as well. So that's always good. But anyway, we know it's going to be 3/2 NR. And then we take the temperature at C minus temperature at B, just like what we saw before. And substituting numbers, no big deal. 3/2 in this one, R's R, temperature at C. Oh, let's grab here. Oh, 8,000 over R. Temperature at B, 32,000 over R. And once again, R cancel. And as you expect, you're supposed to get a negative number here. Because coming down from B to C, you are coming from a higher line isotherm to a lower line isotherm. Yeah? As expected. All right. And this gives you a negative number. Very nice. So is a negative, what was that? Negative 36,000 joules. If my math is correct, 24. Okay. Nice. And from first law of thermodynamics, of course, heat from B to C will be the delta U plus W automatically. So lovely. Work done is 0. So definitely that is exactly the same number right there. So let me use the same color here. There you go. So that complete what is going on the BC process. Work done is 0. Delta U is negative. Heat flow is negative along with it. Yeah, we see the 3 quantities get calculated. Right, yeah, all right. Pretty good, pretty good. All right, you guys want to try the last portion of this? ทุกคนยัง enjoy ไหม? Is this good? Yeah. All right, C back to A, guys. Or let's do it in red here. There you go. So, going from C back to A. The good news about this one is delta U is definitely gone. Right? Because it's an isothermal process. All right. When one of the term is gone, everything is going to be nice. What else? The work done going from C to A. Oh, it's an isothermal process, guys. Come back here. All right. We have seen this a couple of times before. We can use this notation, this formula to figure out what is the work done during this isothermal process right away. So let's use that. Is an nRT log V final. You go at A as the final point and C as the initial point. So you start with the volume at A divided by the volume at C. All right, substitute the numbers. Okay, not bad. In this one, R's R. The temperature you already figure out is the 8,000 over R. That's your temperature. And then you set the log of your volume shrink 4 times. Let me put 1/4 on here. Everyone good with this? Okay, all right. So you just take the volume, but the volume at A is just 1/4 of the volume at C. So it's going to be 1/4 ratio for sure. Okay, 0.01 divided by 0.04. All right. So R cancel again. So over there, you get negative work done as expected is a negative 8,000 log 4 joules. Nice. Woo. Not bad, not bad. And the reason that you're expecting a negative work done is because it's a contraction. Gas get compressed from C back to A. Wow. All right. And once again, the last stop of this one is what about heat, Ajahn? Heat is going to be delta U plus W. But this time, there is no internal energy change. So whatever the work, it's going to be the heat. So the heat is exactly the same as work, negative 8,000 log 4 joules. Very nice. And that completes this segment here. You get the delta U, you get the work done, you get the heat flow. Wow. And from these, you can now answer part C and D easily. You will be able to tell what is a heat flow, is it in or out? All right. But just to confirm that you kind of get all these pictures here. All right. We're going to show you a little bit of just like a top up diagram here. All right, guys, one more round. Let's look at the AB process. Look at the heat. Heat is positive during this process, right? 60,000 joules. When it's positive, it means heat flow in. The way that we can depict this is, Ajahn, there is a heat flow in QAB equal to 60,000 joules. Everyone good? I put an arrow just to showcase that there is an inward heat. And I just use the enclosed area to be like a, think of it like an internal part of the system. Sort of. Now try again. Look at the BC process. BC has a negative heat. So heat actually leave the system during the BC process. So that is the BC heat. Okay, good. All right. And when you do the C2A, it's another negative heat. So that means heat also leave the system during the CA process. Okay. All right. Get a point here. Well, okay, then you can overlay those heat that just got calculated on top of a PV diagram as well. So that's lovely. But what is the point? So everyone sees what is happening here on this PV diagram. Can you see? Here, AB, heat flow in. BC and CA, heat get dissipated out to the environment. This is exactly what your car engine is doing. Make sense? Initially, you have to burn your gas, right? So you get some energy from that combustion of gas, and then you draw in the heat. That is an inward heat, okay? And then during the process, of course, the cylinders compress the gas down, and then you exhaust the valve, and then all this stuff. There was something that is just going on, so you have something else happening on your engine. But no matter what, your engines get hot because the heat actually leaks out from the engine, and those are the QBC and QBA as an example. With me? And if you recognize those problems that we did before, if you try to figure out the total net work done in the process, the net work done is area enclosed. You guys remember that problem here? Okay, so that means this is it. It's a conservation of energy. You draw in the heat, you let go of some of the heat, but there is some leftover. That leftover is the work done. That is the energy that you use to turn the wheel. You run the car, all this stuff. All right, so this is the way that you can use PV diagram, first law of thermodynamics, to explain the heat engine, the engine that's going to use the thermal energy to drive. And next time, we're going to utilize these sort of like calculations, and we're just going to do sort of like a little bit, you know, it's a simple analysis now. How much heat is in, how much heat you have to discard, how much is left for you as a useful work, then you can figure out the efficiency of this engine. Sounds like a good plan? All right, and it's good to know next time you will be able to see what is the best engine in the universe. And answer to the question that I asked before, why can't you use the body temperature to charge your phone, for example? Why not? Yeah, all right. And you will start to see your diesel engine that's supposed to be the best engine that available to human, it only has efficiency of 45%. So every time you run your car, you pretty much throw away energy by more than half. So that's why hybrid is better, EV is probably better. Yeah, so, and now gas getting cheaper. All right. All right, guys. So I hope this gave you an overview, and we have come pretty far in the sense that this is it, right? All of the build up from last week until this point is just for you to be able to calculate everything on this PV diagram. Okay. With the PV diagram, everything seems to be a lot easier to visualize. Plus, you know everything in the components in the first law of thermodynamics. And next time, we're just going to run on this, drive it a little bit further, and draw the conclusion about the heat engine. Sounds good? All right, guys, that is it for today. Have a good day. Yeah, we're good.